Okay, torque is basically the angular equivalent of force. We symbolize it with the Greek tau symbol, and it's equal to the force applied times the radius at which that force is applied times the sine of the angle at which that force is applied to what we call the line of action, or basically the radius, the angle it makes to the radius. So let's just try this here. Alright, we have 150, and by the way, yes, it's measured in Newton meters, because force is measured in newtons and radius will be measured in meters. So if 150 Newton meters of torque are applied to turn a bolt, what is the shortest the wrench can be if I'm applying 200 newtons of force? So basically I know everything except for the radius. Now the maximum torque is always applied at a sine of 90. So unless you're told otherwise, we assume a sine of 90, which in reality you can just leave off because sine of 90 equals 1, and 1 times anything is itself. So it's best to always use this equation here. Sometimes you'll see the sine theta left off and a little perpendicular symbol put in there instead. I think that's on the AP equation sheet as well, along with this equation here. But this is probably the best way to think of it, because sometimes you do get the force applied at angles, and so just remember that if theta is 90 degrees, that gives you the maximum, and that's just equal to 1. So 150 Newton meters of torque equals 200 newtons of force applied times an unknown radius at an angle of 90 degrees, and when we solve it for R, we get 0.75 meters. Not the best artwork Eric Sampson's ever done. That's supposed to be an engineer on a train pulling on some kind of a lever thingy that's 1.4 meters long. And if you notice, here's what we call the line of action, and his force is being applied at an angle of 70 degrees to that line of action. So the maximum torque rather, would be applied if he had done it at 90 degrees, but given his position, he's going to have to apply it at 70 degrees. So we just substitute into this equation and see what we get. So the engineer is generating 450 Newton meters of torque are necessary to apply these brakes. So that's 450 Newton meters of torque. We're looking for how much force the engineer have to apply. The radius of the device is 1.4 meters between where he's applying his force and where the torque is being applied. And the angle is 70 degrees to the line of action. Solve that for force, we get 342 newtons. Alright, now we've got two weights hanging on a massless rod. And what we want to find out is, what are we trying to find out here? We have a 2-meter long massless rod from our massless frictionless supply store. And we have a 5-kilogram mass that is suspended 0.2 meters from the left side. The rod itself is suspended 0.6 meters from the left side. And the 3-kilogram mass is suspended 0.5 meters from the right side. And now the way we approach this is the pivot point, so the radius will be measured from here. And since the rod is massless, I don't have to concern myself with these two masses. Now remember, it's really not mass, it's not what I'm looking at, it's force, so I have to say mg here. So this is basically going to be our old mg. That gives us 50 newtons here and 30 newtons here. And so what I have to figure out is what is the distance between where this force is applied and here. Now it's applied at a 90-degree angle, so sine of 90 is 1. That makes things a little bit easy for me. But this distance here is going to be 0.4, and then this distance here is going to be 0.9. Okay, so let's just try this, because basically what I have here is I have 1.4 minus 0.5, which gives me 0.9. So we want to see how much torque is produced by each mass. So the 5-kilogram mass suspended here, 50 newtons at 0.4 is going to produce 20 newton meters of torque, and 30 newtons at 0.9 is going to produce 27 newtons of force. So since this torque is greater than this torque, we will get a clockwise rotation of the system. Now, how far from the string would the 3-kilogram mass need to be placed in order to keep the rod from rotating? In other words, what we want to have is for the two forces to equal each other. So, in other words, we want there to be zero net torque. So you could set it up by saying, well, this is clockwise, so that's a negative torque, and this is a positive torque since it's causing a clockwise rotation, a counterclockwise rotation. And so you could set up this way, which would give you this. Or you could just say, well, you know what, if I'm going to get zero torque, that means the torque in one direction must equal the torque in the other direction, and just put them on either side of your equality symbol. Either way, what we're going to get is we want to find out what distance, x, should this be away. We'll assume that the line of action is at 90 degrees, so we'll just say 50 times 0.4 times sine of 90 equals 30 times x times sine of 90. Solving for x, we get 0.66 meters. Instead of being 0.9 meters away, we'd have to move it a little bit closer, and that makes sense. That way, if it's rotating this way, if we move it a little bit closer, it'd have less torque. Now look what we're going to do. Oh boy. Now the rod has a mass of 0.4 kilograms. I'm sorry, of 4 kilograms. And now we want to know how far should the 3 kilogram mass be placed in order to keep it from rotating. So now the way I'm going to set up is I'm going to say, alright, first I've got to figure out where is the, how much torque is being applied by the rod itself. Now, so I have basically a 40 Newton bar, and it is going to have its center of mass is where gravity is applying the force. So when gravity applies a force to an object, it essentially applies it as though it's only acting on the center of mass. So that's going to be 2 meters. If it's a 2 meter rod, it's going to be at the 1 meter mark, which is going to be 0.4 meters from this point here. So between here and here, that's 0.4 meters. So I'll put that down there. That's 0.4 meters. So that's going to apply a torque as well. So 40 newtons acting at 0.4 meters is going to apply a torque in the clockwise direction, and so is this mass here. Whereas the 50 newtons acting at 0.4 in this direction are going to apply our counterclockwise torque. So let's just see how we're going to set this up then. So we're going to say 50 newtons at 0.4, causing it to rotate in the counterclockwise direction. Here's the rod. It's got a weight of 40 newtons, and it's positioned 0.4 meters away from the string, which unfortunately I didn't mean for it to be 0.4 when I set up this problem, but oh well. And so therefore I want to know, where does this one have to be? So the sum of the forces on this side, the sum of the torque on this side has to equal the sum of the torque on this side to keep it from rotating. So 20 equals, that works out to be 16 plus 30x. Now I'm just going to subtract this from both sides, gives me 4 equals 30 over x. 4 divided by 30 gives me 0.13 meters. So I would have to take this mass and move it so it's 0.13 or 13 centimeters away from this string. Okay, we have a constant force applied to this oddly shaped piece of metal, let's just say. And what we want to do is we want to rank these from, and ranking tasks are a fairly common problem you might get exposed to on the new type of AP question. So basically what we want to look at is where is the smallest and where is the largest torque going to be. Since torque equals the force applied, and we're told this force is constant, so we can ignore that, what we have to pay attention to is the radius and the angle. If the angle is anything other than 90, it's diminished. So 90 is the greatest, and then the larger r, the larger the force. So the one that's definitely going to have the least is B. Since it's acting through the center mass of the system, it essentially has a radius of 0, so that has to be the smallest one. C is the next farthest one away, so I can put that here. Now I've got, for the next two, what I'm going to do is I'm going to draw the line of action here. So here's the line of action for this one, and here's the line of action for that one. And you can see that D makes less steep of an angle to it than A, so therefore it's closer to being at 90 degrees. So that one is going to be greater than A, so I'm going to put A here and D here. Now let's look at these next two. Alright, what I have here is a rod. It's 6 meters long, so its center of mass is at 3 meters. Maybe I should write that down. 3 meters, that's a terrible 3 meters. And it is at an angle of 30. It's held at an angle of 30 degrees. It has a mass of 85 kilograms, which gives it a weight of 850 newtons. And it's held in place by the string here, which makes an angle of 60 degrees to the line of action. And so basically what we have is a system where I have one torque is causing it to rotate in a clockwise rotation, and this is another torque causing it to rotate in the clockwise rotation, and the two are balanced so the thing's not moving. The torques are balanced. So what we'll do is we'll first figure out what this torque is. It's going to be 800 newtons applied at a distance of 3 meters at an angle of 30 degrees, so the line of action is 30 degrees, and that has to be equal to this torque, otherwise the system would be rotating. I don't know what the force applied by that string is, that tension force is, but I know it's acting at 6 meters and at an angle of 60 degrees to the line of action. So once I set this up, I simply solve for F, and I get 245.4 newtons. So it turns out to be a lot easier than it looks at first. You got to be a little bit careful with this next one because we have a rod that has weight as well as the object hanging here. So we have a tendency to want to just focus on this, but you have to remember that this is not from our massless, frictionless supply store. So what we have is a 1 kilogram rod. So if this is a 1 kilogram rod, it's applying 10 newtons of gravitational force acting on it. And it's acting at the center of mass of the system, where gravity acts as though it is a point force acting on the center of mass. And since this rod is 4 meters long, that gravitational force is going to be applied at the 2 meter mark, at the center of mass. Okay, so with that in mind, let's just see what we've got. What is the net clockwise torque on the system? So the clockwise torque on the system is going to be applied, there's two things doing. It's the sum of this mass here, which has a weight of 30 newtons, which is acting at 3 meters. So I have 30 newtons acting at 3 meters at an angle of 90, plus I also have 10 newtons of force acting at 2 meters, also at 90 degrees. So I have a net clockwise torque of 110 newtons. Now I want to know what is the tension on the cable. So to find the tension on the cable, I just say, well, the two forces have to be equal, otherwise the system would be rotating. So I take the 110 and put it over here. So because I have to have 110 newton meters of torque in the counterclockwise direction to keep the system motionless. So 110 equals the tension on the string times the distance at which it's being applied, which is 4 meters, times the sine of that force to the line of action, which is 30 degrees, 55 newtons. So really these problems at first look really cumbersome, and in fact with this awesome equation they're quite easy.